Download this code from codegive.com, link in the description below. Unbounded knapsack problem, 1D array space optimized approach. The unbounded knapsack problem is a classic problem in dynamic programming. The problem can be stated as follows. Given a set of items, each with a weight and a value, determine the maximum value that can be carried in a knapsack of a given capacity. Unlike the 0/1 knapsack problem, you can use an unlimited number of each item. Problem definition. Input. An array of weights where each weights I represents the weight of the ith item. An array of values where each values I represents the value of the ith item. An integer w representing the maximum weight capacity of the knapsack. Output. The maximum value that can be obtained with the given items and weight capacity. Dynamic programming approach. Steps to solve the problem. 1. Define the state. Let dpj be the maximum value that can be attained with a knapsack capacity j. 2. Initialize the state. dp0 equals 0, when the capacity is 0, the maximum value is also 0. For all other capacities, initialize dpj to 0. 3. Recurrence relation. For each item, if you can include it in the knapsack. Backslash. dpj equals \max, dpj, weights I plus values I. Backslash. The iteration continues for each capacity from the current item's weight to the maximum capacity W. For result. The answer will be in dpw. Space optimization. Instead of using a 2D array, we can use a 1D array to save space since we only need the previous results stored in dp. Code example. Here's a Python implementation of the space-optimized approach for the unbounded knapsack problem. Explanation of the code. 1. Initialization. We create a list dp of size w plus 1 initialized to 0. 2. Outer loop. Iterates through each item, weights I, values I. 3. Inner loop. For each capacity j from the current item's weight to w, we update dpj by checking if including the current item results in a higher value. 4. Return result. Finally, we return dpw, which contains the maximum value that can be achieved for the given capacity. Complexity analysis. Time complexity, O, n*w, where n is the number of items, and w is the maximum capacity. Space complexity, O, w, due to the use of a 1D array. This method effectively reduces space usage while maintaining the same time complexity as the traditional dynamic programming approach.